All right, so in section 10.1, we looked at systematic listing as a way of making a list of, but then also ultimately counting how many options we had given certain criteria or conditions that we were meeting in certain cases. And we're going to continue that today with a process called the fundamental principle of counting. And the first thing that I need to make you aware of, in case you haven't seen it before, is just a little bit of notation. And that notation is a factorial notation. So it looks like an exclamation point. So the n that's listed there are our counting numbers, or our natural numbers, which we've talked about before. And when we see n factorial, it means we take whatever number that is and we multiply it by the number 1 less than that, and 1 less than that, and 1 less than that, all the way down to the number 1. So it's a multiplication process of a whole bunch of numbers from n down to 1. And by definition, we're defining it to be this way, 0 factorial, which doesn't fit in up there because it's not a counting number, but 0 factorial is equal to the value of 1. So working with factorials involves multiplication. And we're going to see quickly, too, it's going to involve reducing fractions. All right, so we're going to take a look at some examples where we see these processes working. The first one is just simply 5 factorial. So what we're going to do is we're going to take the number 5, and we're going to write out all the values that are less than 5 multiplied out. So 1 down from 5 would be 4. And then down from that would be 3, continuing down 2 and 1. And we stop at 1. So we always stop with the number 1 in this multiplication listing. All right, so if you want to grab a calculator, if you want to multiply it by hand, it doesn't matter to me, but we need to multiply out 5 times 4 times 3 times 2 times 1. And what will we get? Yep, 120. So 5 factorial is equal to the number 120. Okay, so as we're working with these, the next one actually has some division in it. We see a factorial, we see one on top, and we see one on bottom. A word of caution as we're working with these, you can't just reduce the 8 and the 4 where they are when they have a factorial after them. So I can't just say, hey, look, there's an 8 on top and there's a 4 on bottom. They have a 4 in common. We're just going to cancel them, and the 8 on top is going to become a 2 factorial, and we're done. It's actually not true. We need to write them out, and we actually can write them out until they match. So let me show you what I mean by that. So this 8 on top can be written all the way down to 1, like I did with a 5, but I'm not going to do that. 8, 7, 6, 5. And I'm going to stop at 4 factorial, and the reason I am is because notice, if I were to write out the 4 factorial, it'd be 4 times 3 times 2 times 1, which is exactly what I'd have on bottom. So if they match exactly, not just factored like I can factor something out of them, but they match exactly, I can stop, and then I'm able to cancel those pieces out. If you don't want to do it that way, you can write more of them out, but if the numbers are quite large, that's going to be impractical. This one you could do it for if you wanted to write everything out. It wouldn't be a big deal. So you're going to multiply then 8 times 7 times 6 times 5. So what value does that give us? Anybody?
1,680.
Thank you. Yes, 1,680. Okay, so it's helpful to be able to reduce these. We don't have to do as much work if we notice something matches, right? Cool. So we're going to get a little more complicated as we go. So the next one actually has 2 pieces in the denominator, right? We're going to do the same thing. It's just that only one of the 10 factorials in the denominator will cancel. So I'm going to write out my 20 times 19 times 18, and I'm going to keep going until I get to 10. 17, 16, 15, 14, 13, 12, whoops, here we go, 11, and 10 factorial. And it doesn't matter which of the 10 factorials I write on bottom. I'm just going to need one of them, so I'll just write the one at the back. The other one I have to write out, just like I wrote out the 20 till I got down to the end. Okay, so one of my 10 factorials I've rewritten already over here. The other one I'm going to actually write all the details out for them. So I have 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, and 1. Is that okay? Right? So, of course, the point in that is that the 10 factorials will cancel. You have two choices. If you want to multiply everything on top and get a value and write it down, and multiply everything on bottom and get a value and then divide them, you can do that. Sometimes, and this may be the case, the number will be too large and your calculator will turn into scientific notation, and that's not helpful in the slightest. So I'm going to presume that at some point that's going to happen, so I'm going to show you what happens if that's the case. All right, so the thing is, when I'm working with factorials like this, everything in the denominator will cancel with something in the numerator. So this is going to be a whole number when I'm done. If you get a decimal or a fraction or something, there is something that went wrong along the way. Probably your calculator approximated something if you've used your calculator a lot in the particular problem. So you can pair things up. That's one way to deal with it. For example, if you notice, we have 10 times 2. There's a 10 here, and there's a 2 here, and 10 times 2 is 20. So I can actually cancel the 10 and the 2 on the bottom with 20 on top. So if you happen to pair things up and they cancel completely, that's great. Not all of them are going to do that. For example, I don't have 9 times anything that's going to cancel, but the 9 cancels with something, right? I mean, the 9 with the, say, 18 in the top will cancel out. 18 divided by 9 would be 2, so that's going to leave me a 2 on top. The 8 and 3 was still too big, so I need to do the same thing with 8. 8 and 16 would be great. And we're going to happen to get another 2. They don't always become 2s, but this one did. How about our 7? 14 would be good, yeah. 7 and 14, there's a 2 there too. 6 and 12, sure. Now, if we had noticed it earlier, the 6 and the 3 would have been 18. I could have completely canceled it with 18. That's fine, but I don't have to do it. There's no specific ordering to what we're doing. We have lots of flexibility. So 6 and 12 is what Graydon said, so that one will work. So 6 and 12 gives me another 2. What else?
5 and 3 weeks we done.
Ah, so I have a pair. The 5 and the 3 actually make my 15, so those are going to cancel completely on that one. So that's good. And I need 4 to cancel with something. So you have options, but notice if I would like, I can take 2 of these 2s and cancel it with the 4. Can't I? We're just looking for things that divide. We'll do more examples. We're just looking for division factors, okay? So we're needing to figure out what's remaining, though, and it's really easy to sort of lose numbers along the way, so be very careful. There's a 19 and a 2. I'm just going to write them down one more time so that I'm being careful. We have a 17, and then there's 13. And then I have a 2 and an 11 at the end. So being careful to make sure I've captured all the pieces that are still in my list that didn't get canceled. I think I caught them all. And we would take calculator and we'd multiply those together. So 19 times 2 times 17 times 13 times 2 times 11. It's going to be a larger number than we've had so far. Somebody tell me what you get when you get there.
$184,756.
Okay. So that's what I have on mine too. Did anybody else get that one? Yeah? Okay, good. So this is what we would have when we've completely simplified all this. Yep, great.
4 cancel out with?
2 2s on top. Yeah, I used 2 2s because at that point I didn't have any other even numbers that it divided evenly by, so I combined 2 of the 2s on top. Yeah. Okay, so number 4 starts out looking different, but it's really not that different than the last one. We're leading up to something, that's why it's showing this. So there's this notation that looks a little bit weird. It's got N's and R's in it, but then it tells you what N and R are. So we're just going to put the N and the R values in here, and then it's going to look a lot like the last one we did. So it says N is 28, so that's on top, 28. It says that my R value is 15, so the first thing on bottom is R, so I've got 15 factorial. And then in between here, I'm supposed to subtract the two numbers, so 28 minus 15. Yep, Marquez.
Does the parentheses make a difference?
So it does, like the parentheses I've got right here, because I want to make sure that I do the subtraction first. Technically, without it, like if you had written down 28 factorial, and you have your 15 factorial, and then you need 28 minus 15 factorial, what this would be telling you to do is to find 15 factorial and then subtract these two quantities from one another. But that's not what I want to do. I want to subtract the 28 and the 15 first, right? So parentheses are grouping symbols telling you what we do first. Yeah, so we don't want this. Let's actually start with the subtraction, though, since we've highlighted the fact that that's important. What is 28 minus 15? No. 13, yeah. So I have 28 factorial on top. I have 15 factorial and 13 factorial on bottom. Okay, everybody good?
So we don't multiply.
We are, but we're not there yet. Yeah, we need to actually distribute them all out.
Before we get out.
Right, so this problem actually looks like where 13 started now. I've got a single number on top with a factorial. I've got two numbers with factorials on bottom. And interestingly enough, do you notice that both of these have the same sort of pattern, and we'll see where it's coming from in a moment, that the two numbers, 15 and 13, add to 28, just like the two numbers 10 added to 20? There's a reason that's showing up. It's just we aren't there yet, so I'll show you in a moment. All right, so we're going to write the 28 out, just like I wrote out my 20. And we're going to stop at the biggest value on bottom, 15. So I'm going to write 28 out until I get to 15 factorial, and I'm going to stop. So 28 times 27 times 26 times 25 times 24. I'm going to run out of space. I'm going to shift a couple things around. Oh my goodness, I'm still not going to have enough space. Can you see that 15 over there in the pink?
Couldn't you drag it out to 13 and then just take out the bottom?
Well, you can, but you can only take one of the bottoms out, so I might as well stop with the first one that matches. Whoops. So the 15 factorial that's down here matches with the 15 at that point. If you went out to the 13, it wouldn't hurt anything. It just means that you'd be expanding the 15 factorial instead of the 13. So we are going to cancel the 15s. If you want to just mark that, you can. But the 13 needs to be written out as well. So we've got 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. All right. So I know there was questions in the back over here, like, where did everything happen? You lost me really fast. So we're going to do another one. So what we're looking for is we're looking for either things that we can kind of pair together in the denominator that multiply to something exactly on top, or that reduce. For example, the 13 times 2 is 26, and there's a 26 on top. Okay? So if you want to, you can cancel the 13 and the 2 with the 26, and they all go away at the same time. we run out of the ability to do that with the biggest number because the 12 and the 3 can't do that, right? That's too large. But 12 does cancel with something. 24, so not cancel exactly, but it reduces. So the 24 on top and the 12 on bottom will reduce because they can both divide by 12. So when I do 12 divided by 12, it goes away, and 24 divided by 12 would leave me with 2. I'm going to try to change colors as I go so that we can kind of see what's canceling with what.
Do the 6 and the 4.
Sure, and you don't have to go in order. Yeah, so you could do the 6 and the 4. So 6 times 4 would be 24. Yeah, so if we had...
28, so that'd be better. 5 and 4 makes 20.
Yeah, okay, so let me pause just a second. So Graydon's, I think, saying he had noticed the 6 and the 24 before I messed with my 12. And if you had, and you said, okay, look, well, the 6 and the 4 could cancel with my 24, and you would have canceled that first, that would have been fine. At this point, I've already canceled in the orange, so I'm not going to undo it. So what did we notice next?
6 or 5 times 4.
Okay, so 5 times 4 is 20. So yeah, I can do the 5 and the 4, and those will cancel with the 20. Did you find it a better one you liked?
The 28th, then it gets rid of that big number.
You coulda.
Just divide the 20 by the 10.
Yeah, okay, so somebody tell me another one you see. We can go in order, whatever order you like.
7 and 3.
7 what?
7 and 3.
7 and 3. Oh, yeah, I skipped my C over here. So here's a 7 and here's a 3. So 7 times 3 is 21. So there's a 21 on top, so we can do that one, sure. So 7 and 3 with the 21. All right, what do you want to do next? Somebody said 11. 11 and what?
22.
Sure, 11 and 22 will work. So my 11 here and my 22 here would cancel and give me a 2.
You can divide the 27 by 9 and get a 3 on top.
Okay, so I can take the 9 on bottom and the 27 on top. So the 27 here divided by the 9 would give me a 3.
Same with the 6 and 18.
Okay, we can do 6 and 18. All right, so let's do 6 down here. And the 18 also gives me a 3. There's at least one more that divides very nicely.
8 and 16.
Yeah, the 8 and the 16 as well here. Yeah? So I can do the 8 and I can do the 16, leaving me with a 2. 10 does not divide evenly into anything the way that we've canceled it so far, correct? But do you see anything that you could use instead if you wanted to? What do the 10 and the 10 and something on top have in common at the very least?
10 and 20.
The 10 and the 20, but I already canceled my 20, didn't I? Something that remains.
Use the 3s and the 2s.
You could use 2s. Yeah, so let's use a 2 for the moment. So there's several 2s I've got written up on top here, yeah? I'll just use this first orange 2. That 2 and this 10 would reduce. They both are divisible by 2. It would leave me with what? 5, and where? On the bottom. So that's a little different than the ones I've just been doing, but it's okay, right? So the 10 becomes a 5, and one of these 2's cancels. But then does the 5 reduce with something on top? The 25, yeah. So you can't add. We're not adding, remember, we're multiplying. But it will reduce with the 25. So we can cancel it with the 25. So this 25 will become a 5. So there's always everything on bottom canceling out, always. Great.
Oh, no, I see.
Okay. And it doesn't matter the order in which you do it. So when you guys were over here saying, wait a minute, I saw 14 and a 28, and Graydon was like, wait, we could have done the 12 and the 24. You could. You can do it in any order you wish. And it will all yield the same answer when you're done. As long as you're being careful not to lose any of the pieces. Because let's be honest right now, this is a mess. Isn't it? Really is. And some of you have really messy handwriting, which means it's messier than I've got on my screen right now. Agreed? So be extra careful if that's you. You know if it's you. It's not a surprise. So we're just going to go down the list and try to find all the pieces that are still there. And I'm going to highlight them. Let's go with, I'll hide them in red because I don't have a red used yet. Okay, so I have 28. I have 3 and 5. So times 3 times 5. Let's see, there's 23 and a 2. Times 23 times 2. 19 and 3. And I'm highlighting them so that I know that I've caught them, right? Do you see that? I'm marking them off as I go. That's really what I'm doing with my highlighter. 17 and 2. And I think I got them all. Is everything marked out somehow?
The one at the end?
The one at the end, this one?
Yeah.
The 15 factorial?
No, on the bottom.
On the bottom, the 1. True, but what is division by 1? It's just the same thing. So even though we write this all the way out till times 1, the times 1 is never affecting anything. So that's a good thing to notice. All right, we're going to grab calculators. This is a long expansion of numbers to multiply. I don't think you want to do it by hand. Does anybody have an answer yet? Bigger than that. It has my paper.
374 then?
That's too big. Maybe I should double check. My paper could be wrong. You have 37 million as well? I might have a typo on my paper.
Yeah, I think something.
Well, 2 of you got it, so you're probably right. Just need to adjust my answer key. 5 times. Yep, you're right. I have a typo. Okay, so we have 37442160. If I go from the right to the left, we do have 37,442,160. It's big, right? Yeah, it's big. Any questions on that? Okay, this is all leading up to using this inside of a couple things showing up in the next couple lessons. The first thing that we're going to use is the title of our lesson, which is called The Fundamental Counting Principle. For a task consisting of K separate, that's the word I wanted, K separate parts, where the number of ways to do the ith part is n sub I, then the number of ways to perform the task is n sub 1 times n sub 2 all the way to n sub k. An example will clear up what all the details here are meaning. Just jot it down for now. Okay, so are any of you fans of Sonic? We drink Sonic drinks. Sonic's a big deal with my kids. We only get them once a week because they keep getting more expensive, just like everything else right now. And Sonic is a really good example of this. So let's pretend for a moment, and then we'll do the examples I actually have written down, that you're going to Sonic, and like you're one of my kids, you're going to Sonic with me, and I say, okay, you can get one soda or tea or whatever, right? One drink, and then you can add 2 flavors in, okay? So what do? Well, first you got to pick the drink. That's one of these K tasks, right? Well, you got lots of options. Maybe there's like 52 options. There's probably not that many, but there's a lot at Sonic. You got that many options. And then you've got all the flavor add-ins, right? You have all of these flavor choices that you can add in, from strawberry to caramel to nerds these days, right? All this stuff that you can add in. That's flavor number one. So that's your second thing that you're doing. So this N1 would be representing how many different flavors of drink there are. And then N2 would be representing how many different add-ins you could put in. And if I told you could put in 2 add-ins, then you would do it a second time. How many add-ins you're still left to choose from. Okay? That's what's going on here. You're creating something where you have multi-steps along the way. When you get up in the morning, you put on an outfit, right? So you've got your shirt, you've got your pants, you've got your shoes, you've got all your undergarments, and the combination of all those things is this again. How many options do you have for each one of those different pieces of clothing that you put on? It's a fundamental principle of counting. So we're going to do some examples where we're creating committees like we did before, because we saw these earlier, right? All these folks yesterday. And we were looking at how many we had at the end. So if you have those written down from before, you'll be able to, after class, or even right now if you wish, compare that we're going to get the same thing. We just don't get a list. We only get the number. So it says that we've got our group of students, or kids, and they're having ways of forming the following groups. And the first one is the same one we saw yesterday, president and treasurer not of the same sex. So the first thing that we actually have to choose is how many different people could be president. So with these conditions, how many people could be president? All of them. And there are 6. We have 6 different presidents, right? This is my president role. After I've picked a president, though, they can't all be the treasurer. In fact, none of them can be, right? So if I didn't have this condition about the same sex thing and it could just be anybody after that, I would have 6 and then I would have 5, because I'd have all 5 people being viable options for the second choice. But that's not the case on this one. Once I've chosen this person, in this scenario, I have the same number of boys and girls. So in this scenario, once I've picked that person, I eliminate everyone else of that same sex from being, chosen for the next position, correct? Yeah. So how many choices do I have for the treasurer if I have created that already? 3. Because there's 3 different people of the opposite sex that did not fit in with that description. And the fundamental principle of counting says, what I'm going to do is I'm going to multiply these results together. So we have 6 times 3, which gives me 18 ways. And if that's all I cared about knowing is how many ways there are to do this, that's a lot faster than what we did last time, isn't it? Absolutely a lot faster. So we can continue this process again with the next one. We're doing all 3 that we did last time. President, secretary, treasurer. President and treasurer are women. Okay, so again, I like to put like lines representing my locations here. So this is my president, this is my secretary, and this is my treasurer, just like we did last time. It says the president is a woman. So how many women do we have on this list? 3. And it also says that the treasurer is a woman. So how many women do we have left to pick from? 2. So nobody's going to hold both roles. That's the underlying assumption, of course, here. And so we've got 2 people left who can serve as treasurer. But secretary didn't have any conditions, correct? So after I've chosen my president and my treasurer, how many more people are left that could be secretary?
3.
Is it 3 or is it 4?
4.
It's 4. All the boys plus the one girl that didn't get picked for president or treasurer, right? There's 4. And we multiply 3 times 4 times 2. So what is 3 times 4 times 2? Okay, it can't be 27. It's got to be even. 24. Yeah. 24. Close. So 24 ways that we could do this. And again, if you look back, that's exactly what we got when we listed them all out. But now we did it faster, if all we care about is the number of them. The last one I actually alluded to a little bit already. Talked about a committee. So when we're doing a committee of 2 people, we've got a couple of things that happen. First of all, I have the 2 positions. They're 2 different choices that I'm going to make. How many people can be in the first location? 6. And how many can be chosen in the second location? 5. Got to be 5. Okay, because we've got to have 2 separate people on the committee. Yeah.
Is it pretty much just going down on one, it's like this 6 is already one person?
Exactly, yeah, so we've already used up one of those people, they're already on the committee, I have 5 more to be able to be on the committee with that person. But if I multiply these, 6 times 5, I get 30. Do you remember what our answer was on this? Because it wasn't 30. Our answer was 15. So why was our answer last time 15, but so far on this problem it's 30? Well, right now, because I've written my 6 and my 5 the way that I've had, it's double counting everything. You know, I've got David and Nate, you know, in the position David, Nate, and I've also got Nate, David in the position Nate, David. But that's the same committee. So when I'm working with a committee, I have to keep in mind that there are double counts that have to be removed. So how do we remove double counts? Well, we just divide by 2. So this removes a double count. And sure enough, if I take my 6 times my 5, which is 30, and divide by 2, I get 15, which is exactly what I had last time. 15 different ways this can happen, or 15 different committees, whatever. Okay, so I wanted to show you the connection with what we did before and how this can be used and makes the process a lot quicker. And at the very least, you could use this to verify that what you did in section 10.1 was right, couldn't you? Yeah, you could make sure that you're getting the number you're supposed to be getting, that you didn't miss somebody when you listed everybody out with the listing method, those kinds of things. But we're going to look at a few other ways. We're going to actually look at testing. So you all take tests in all kinds of classes, all kinds of tests, right? So we're just going to look at a few different examples of tests, and these would be more like quizzes because they're short. So imagine that you have a 6-question, it's got to be a quiz, can't be a test, right? 6 questions. Determine the number of ways to mark your answer sheet when you have 6 questions that are true, false. So if there's 6 questions, it's like over here where I had 2 committee members. I need 6 blanks, okay? So I have 1, 2, 3, 4, 5, 6 different blanks because there's 6 questions. And I'm trying to figure out how many different sort of, answer keys could come out of this if it were sort of randomized or if you were randomly guessing. So how many different choices do you have on a true-false test? 2. And it's 2 in every single location because they're all true-false with this scenario. And so we would multiply 2 times 2 times 2 times 2 times 2 times 2, 6 of them. What would you get? That's adding. We want to make sure we're multiplying. It's 64, yeah. So do be careful because that's a really common thing to do is just to forget which operation we're working with. This one's multiplication. So there are 64 ways.
6 squared? I mean,
It's 2 to the 6th. Yeah, this is 2 to the 6th if you want to think about it as an exponential notation, yeah. So if you're just randomly guessing, you're probably not going to get all the answers right because there's 64 different ways that that answer key could show up that the professor has made, right? And that's just with the true-false test. So let's change it now to a multiple choice test where there's 5 answer choices. Still have 6 questions, but what goes in our blank now? 5s. Every answer has 5 choices, or every question has 5 answer choices. And we're multiplying then, and much like Graydon just noticed, if the last one was 2 to the 6th, this one is 5 to the 6th, if you prefer to write it that way in your calculator. What would you get? It's bigger than 64. How much bigger?
15,625.
So the answer is actually a lot bigger, right? So you may find yourself liking multiple choice tests from the standpoint of being able to select the right answer. It's not as sort of like hit or miss, maybe. But if you absolutely have no idea what's going on going into it, this is not your friend. Marquez.
Okay, so on the top one, we
Yep.
did 2 to the 6 power.
Yep.
So like, why do we do the 2 instead of like 6 squared?
Because there aren't any sixes. It's not 6 times 6, it's 2 times 2. So multiplying a bunch of 2's together, this is actually notation for what it means to have exponentials. So when we multiply a number together a bunch of times, that base stays the same, and it's the exponent that tells us how many times we did it. Okay, I think there's a couple more.
Okay.
Yeah.
On number 9, when I get number 8, whenever it's 2, because like you only have true and false as your answers. But for number 9, how did you know that it was 5?
Because it says so in the problem.
Alright,
That's all. Yeah, it would have to tell you, because we wouldn't know, right? Because not all multiple choice tests have 5 answer choices, so you'd have to be told. Yeah. Okay, next one. Matching. Have you ever had matching tests? Okay, so this is the matching test where, you eliminate them as you go, which is much preferable to the ones where they might be able to show up in multiple places or not at all. Those are also disconcerting. So our premise is that there are 5 matching pieces, and there's 5 numbers or values or whatever in the answer, in the test bank. So we have, I don't mean 5, 6, I think it said, right? No, this one's a 5-question test. It was. So there's only 5 questions now. 5 questions, there's 5 answer choices. So how many answer choices do you have when you first start the test? Well, there's only one that's right, but how many choices do you have to choose from? 5.
Just turn that.
5, yes. And then once we've used it, we eliminate it, right? You mark it off. This is how you take a matching test. You mark it off, and then you go down from there. And now you only have how many choices to choose from the second time? 4. And you may not necessarily be going in order if you know what you're doing, right? Some of them you know better than others and those kinds of things, but this is a randomized question. How many answer choices do you have for your third one? 3. And then your last one is, and that should look familiar. If I were to write that kind of like I did over here with 5 to the 6th, 2 to the 6th, what is the abbreviated notation for what I just did here?
5 exclamation point.
Yeah, the 5 factorial. And we actually did 5 factorial before. It was 120. So that's where it's coming into play from what we had seen before. It'll come into play next class period too. Okay, last one. You ready? Okay, so this one had 5 questions. There's an answer bank of 5 answers. But we change it up because this is what you see happen on tests sometimes too, right? You have 5 questions, but how many values or things are in the answer choice bank, the test bank? More than you need, right? That makes it harder. So how many do we have to choose from when we're making our first selection of choices? 10. And then after that's eliminated, we have 9. And then 8, 7, and 6. And while I don't have a concise notation for what this looks like, we did see this happen. We saw it happen on our second problem that we did today. So if you flip back over to the front page, you have a problem that says 8 factorial on top. I think that's what it is. And 4 factorial on bottom. And what we saw happen is we saw at the very end, it happened to be 8, 7, 6, 5. And those were the 4 numbers we multiplied. So this has a form. You would never be asked to do this, but the form that this actually is 10 factorial over 5 factorial. That's what it is. Because it doesn't have the 5, 4, 3, 2, 1 at the end. Yes?
Could you have done like 10, 1, 4, 7, 6? Like anything between 1 and 10? Or it's...
No, because there's 10 choices, and once I eliminate them, I still have 9 things to pick from.
Okay.
So they're going down by 1 because I've eliminated 1 every time. And if you were doing a test bank where it didn't have, like, you could use an answer multiple times, you wouldn't do that either. You'd write 10, 10, 10, 10 on all of them, kind of like your true false, because you can use an answer choice more than once, kind of an idea. Probably wouldn't use it on everything, but that's how you would do the mathematics for it. All right, so if you grab your calculator, 10 down to 6 multiplied out, what do you get? 30,240 ways. Any questions on that? It's all about randomness, right? Like I get that if you're taking a test, hopefully you know something and it's all not all random on these kinds of tests. But that's the way the questions are being posed. Graydon, last question. Yeah, what do you got?
On Mathway, are we gonna have to set it up like 10/5, like?
I don't remember. I don't think so. I think it's just going to ask the question and you're going to get from like this question and then you're going to put this answer in. And the catch to that means that I have no way to check your work. So be careful. And if you're sending me questions, make sure you're letting me know what it is you set up. Okay,